Okay, so we were looking at the translation operator. If you remember on Monday, we said that, okay, so let's assume that there is this operator which translates the position kets by some amount dx, and we call that t dx. And we had looked at some of its properties. For example, if you just make two separate translations, we can write it as a single translation. It always has its Hermitian conjugate should be its inverse, so it has to be a unitary operation, this translation operators, because it should conserve probabilities. Probabilities do not change if we just translate our system. The total probability, if it was 1, it is still 1. The total probability should not change. Of course, the probability that the particle will be in a certain region of space will be modified. So if it was in this region with 90% probability, after translation it will be in this region with 90% probability, but this 90% doesn't change. So to guarantee that, it has to be unitary. And furthermore, just translation by the minus a displacement is the same as the inverse of the translation by that displacement. And finally, we were looking at its commutation relation with the position. So it doesn't have to it doesn't commute, because basically whether we translate first or make the x measurement first, the result, or the other way around, the result will change. So that is basically what means that this translation operator doesn't commute with x operator. And we had found that this translation, we had discovered this commutation relation. And then we were looking at, so what is this operator? And to look at that, we were looking at we basically made a Taylor expansion. We already know that no translation is just identity operator. It doesn't change our ket. So when delta is equal to 0, the operator should be 1. And we just make a Taylor expansion. There's a linear term, a second order term, etc. You have all these expansion terms. And then, of course, this k should have certain properties, so that this t has the properties that we had described. So one thing was it has to be unitary. So t dagger t had to be 1, whatever the value of delta is. And when we calculate that, we had seen that t dagger t deviates from 1 by a term proportional to k minus k dagger, and hence that term should be 0, which told us that this operator k had to be Hermitian, whatever this operator is. Well, that tells us that this operator k corresponds to a certain observable. It's possible that we can observe this operator. We don't yet know what it actually is, but it's Hermitian, so it's observable. And then we looked at its commutation relation with the x. The commutation of t with x, we had already derived it. This gave us some constraints on the commutator of this k with this operator x. And just expanding everything up to terms of the order of delta, we obtained that k and x commutator has to be minus I. Now the next question is, what is this operator k? What is the corresponding observable? Well, there's no proof of what that operator k is. We know that it's an observable. We know that it generates translations in the sense that we had discussed on Monday. Well, we also want quantum mechanics somehow to mimic classical physics, because we know that classical physics works, that is in a wide variety of phenomena. So we would like to mimic it. That is, it has to be somehow contained in quantum mechanics. Quantum mechanics should be an extension of classical physics, so that it will not contradict any observation we made that can be explained with classical physics. So what we say is that k is equal to the momentum. Well, let me add a minus sign over here to be consistent with the convention of the book, divided by some constant. Well, in classical physics, the momentum is, have you taken analytical mechanics or classical physics? Have you heard of canonical transformations? For example, in classical physics, momentum is the generator of translation. Well, here this K operator, whatever that is, it generates translation. So just making this analogy, let's say we are kind of borrowing this term that the K should be somehow related with momentum in classical physics. Well, the units don't match. The unit of momentum and the unit of K, they are different. You see, K has the unit of 1 over distance. Remember, T, delta, we had defined it as 1 plus I K delta plus higher order terms. Delta has the unit of distance, so K should have the unit of 1 over distance, which is definitely not the unit of momentum. So K cannot be the momentum, but it can be at most proportional to momentum. And that proportionality constant basically turns out to be h bar. In a sense, you can say that this is an assumption, this is a definition, this is not a derivation. But since in classical physics momentum generates translations, we say that, and in quantum physics, this K generates translations, we assume that K corresponds to the momentum observable. So in this sense, the translation operator just becomes 1 minus I P over h bar times delta plus terms of the order of delta squared. Now this is assuming that delta is very small. Now we can just generalize this, well, this to 3 dimensionals also. In 3 dimensions it will also look more or less the same. The only difference will be this delta will be a momentum of 3 vector. Similarly, for each direction we will have a momentum operator to generate the translations in that direction multiplied with delta. This is the 3-dimensional generalization of the translation operator. Now we know that P, well, we had already derived that K and X commutator should be minus I. This is what we had derived on Monday. And here K is just minus P over h bar. X is equal to minus I, or the commutator of P and X should be I times h bar. Am I missing some sign somewhere? No. Well, there seems to be sign problems somewhere in our derivation. Yes, I mean, that's what I'm saying. So probably this should have been plus. We should go over our derivation from Monday. So this is plus. So this is plus. So Px commutator is minus I h bar. This is the correct commutation relation we have. So this signs over here are correct. The sign here is correct. So I might have missed some signs in the derivation on Monday. This should be plus. Well, so X and P, they do not commute. Well, we have 2 incompatible observables. We had seen that already the variance or deviation or the errors in the X or P measurements, they are related. And we know that delta P squared expectation value in any state multiplied with delta X squared expectation value in any state should always be larger than or equal to h bar squared over 4. Well, since we had derived that it should be larger than or equal to expectation value of Px squared over 4, This is what we had derived before. And so this is, at least in the case of the momentum and position, this has to be h bar squared over 4. So this is the famous position coordinate uncertainty relation. And this is experimentally verified, at least in the case of the atomic spectrum. Now, of course, now you can ask the question, what about the commutator of px and py? Now, in the last lecture, we had assumed that xy was equal to 0, xz was equal to 0. Well, these are operators. And yz, we had assumed that they are all equal to 0. This was an assumption, there is no proof. In fact, we are building models in which we don't make this assumption and they don't necessarily commute, especially if you are working with gravity. It seems that quantum gravity will be contradicting with these commutation relations. But for all other theories, at least within our experimental limits, as far as we know, they do commute. So we can talk about, I mean, we made this assumption when we said that we can talk about the eigenkets that have a definite value of x, y, and z. If you remember, on Monday we had started by assuming that there are such kets. That assumption basically amounts to the fact that the corresponding operators should commute. Now, what about the momentum operators, px, py, pz? Can we say something about that? We definitely had shown that p and x should not commute. Their commutation relation is not 0. But what about the different components of the momentum? Well, let's look at this. Let's take a state. Let's first translate it by delta x in the x direction and delta y in the y direction. This is equal to translation in the y direction by delta y of the state x plus delta x, x hat. Well, this, let me just show it with the vector r. Which is r plus delta x in the x hat plus delta y in the y hat. But this is the same thing as r plus delta y in the y hat plus delta x in the x hat. If we translate first in the y direction, then in the x direction, it should be the same thing. This is the same thing as translation operator, translation in the x direction by delta x of the ket r plus delta y, y hat, which is t delta x, x hat, t delta y, y hat, r plus delta y, y hat. No, there's no delta y, y hat. This is true for any ket, any position ket. Well, this basically tells me that translation in the y direction and translation in the x direction, they commute. Well, we know certain cases where this doesn't hold, by the way. If you translate first in the x, then in the y, it's different than if you translate first in the y, then in the x. One known example is the Hour1 effect, if you are familiar with the effect. If there is a magnetic field in the region, let's say this is a region where you have a magnetic field, and you have a state localized over here. If you make this translation, it is different than if you make this translation. These two states differ by a phase, which is proportional to the magnetic flux. And this gives rise to what's called the Hour1 effect. Now, when you study quantum mechanics in electromagnetic fields, we will be discussing this one. But just for the time being, you will ignore such complications. In general, this is kind of counter to what you would expect. So you would expect whether you translate in the x then y or first in the y then x, you don't expect anything to change. But under certain cases, they do change. Nevertheless, for most cases, we will see that it doesn't really make any difference. So the translation in the x and the y directions, they should commute. Now, if they commute, we know what those translations are, at least for infinitesimal distances. It will be 1 minus px delta x times I over h bar and 1 minus I py delta y over h bar. Well, one commutes with one commutes with this operator commutes with 1, and the only thing left is the commutator of the second terms. So this is equal to minus I over h bar squared delta x delta y px py, and this should be equal to 0 because, well, the left hand side is 0. And this basically tells me that px and py, they commute. So basically now we have what's called the canonical commutation relations in quantum mechanics. xi, xj, let me write it in this form. This is 0. I and j being 1, 2, 3, or x, y, z. Pi, pj, it is 0. Now that we will discuss when we come to the angular moment. And p times x, pi times xj is equal to ih bar Kronecker delta ij. Huh? Yes, minus ih bar. So these are our probably the most important commutation relations we will see in quantum mechanics. Well, just a small note about in rotations. You see, even classically, rotations do not commute. It's not quantum mechanical phenomena. It's a property of the rotations. They do not commute. Let's take this one. Let's say this is the rotation in the z. This is the rotation. This is my x-axis. This is my y-axis. This is my z-axis. Let me first make a rotation in the x direction by 90 degrees. Then make a rotation in the around the z-axis by 90 degrees. This is what you obtain. Short side pointing towards you, and it's vertical. Let's do the other way around. First rotation around the z-axis, then rotation around the x-axis. So it's the face facing you. So this is not a quantum mechanical phenomenon. It's just the rotations, even in classical physics, they do not commute. The order in which you make rotations makes a difference. But if I start from this point, first move by such a distance in this direction, then in this direction, or if I move first in that direction, then in the perpendicular direction, I come to the same point. So the order of the translations we make, it doesn't really matter. But the order of rotations we make, it does matter. It's not special to quantum mechanics. Now, so what about finite rotations? You see, we know that T of delta is equal to 1 minus I delta dot P over H bar, plus terms that we ignored. Now we can derive finite rotations. Let me just use this symbol. Delta not necessarily small. Well, this I can write in this form. We know that, well, let me start by this. This is T delta over 2, T delta over 2. Because two translations is the same as the translation by the sum. I can just generalize this. This is equal to T delta over N, T delta over N, N times. Or T of delta. Now, also keep in mind that that equality holds whatever the value of N is. Whether N is 2, it holds. Whether N is 10, it holds. N is 1 million, it holds. Independent of the value of N. Well, I can just look at T of delta is always T of delta over N to the power N. This equality holds for any value of N. So it should also hold if I take larger and larger values of N. But for N sufficiently large, that capital delta over N is a very, very small displacement. And for very, very small displacements, I know what the translation operator is. One minus I over h bar delta dot p plus terms of the order of delta squared to the power n, where delta, I define it to be capital delta over n. Now let me do one more step. This is equal to limit as n goes to infinity, exponential of the logarithm of 1 minus I over h bar delta dot p plus of the order, terms of the order of delta squared to the power n. Well, exponential of a logarithm is the number inside the logarithm, or the expression in the logarithm. I didn't really do anything over here. Well, now there is one problem though. I mean, these are not numbers, these are operators. And whenever you have functions of operators, we will always interpret them as in terms of their Taylor series. So the logarithm has a Taylor series, exponential has a Taylor series. So these are in fact Taylor series. Now let me write it explicitly. Limit n goes to infinity of exponential. Well, the Taylor expansion of logarithm of 1 plus x is equal to x plus terms of the order of x squared. If x is sufficiently small, I can just ignore the higher order terms. So if I use that thing over here, exponential, this expression is the limit. In that limit, the exponential of minus I over h bar delta dot p plus terms of the order of delta squared. And I'm taking the nth power of this exponential. This is equal to limit as n goes to infinity, exponential minus I over h bar n times delta dot p plus n squared over n times terms of the order of delta squared. Well, you see, n times delta is what I had called the capital delta, my finite translation. This is limit as n goes to infinity, exponential of minus I over h bar delta dot p plus 1 over n terms proportional to n times delta squared, or higher order terms of n times delta. Now you see, this first term is now independent of n. Delta was fixed. This is, I'm looking for translation by delta, which is a finite translation. N times delta is a fixed number. So if I increase the value of n, those terms that are of the order of n delta squared, they do not change. But here I have this 1 over n term, which gets smaller and smaller and smaller. And eventually in the limit, that term just becomes 0. So I end up having t of delta is exactly equal to exponential of minus I over h bar delta dot p. So in fact, this is why in all our derivations beforehand, we only looked at the linear term in our translation. Because when we look at very small translations, we can always construct a finite translation by a very large amount of very small translations. So this is, in this expression, there is no assumption. This delta is an arbitrary translation. So now we also have the translation operator. Now, any questions on this translation operator or the canonical commutation relations we had derived? Now let's define our wave functions. Now we had, when we were defining these position kets, we had said that they are complete. Now let me write it in this form. I will just switch to three-dimensional notation. This is the unit operator. So whatever state we have, this we can always write as d cubed r x, no, r of alpha. This is what we call psi of r. This is my wave function. You see, wave functions are nothing but the expansion coefficients of our kets in terms of position kets. So you see, alpha is just d cubed r psi alpha of r. So integral is nothing but a summation. So you see that when we expand any ket in terms of position kets, position eigenkets, there are some expansion coefficients, and those coefficients are what we call the wave functions. They are no different than any other expansion coefficients that we had discussed before. So we know that, for example, expansion coefficient squared gives us the probability. Well, the wave function squared gives us the probability. Well, since it's continuous, it gives us the probability density. Well, of course, r is a continuous variable, so at every value of r, psi alpha of r can take a different value. You see, psi alpha of r is an inner product of the ket alpha with the ket r. Well, the inner products are always numbers. That is how we define the inner products. So for any value of r, psi alpha of r is a number, is a complex number. So they are what we call functions. You give me a position, it gives you a function, it gives you a number. So wave functions are numbers, ordinary functions of position. Now let's look at the inner product of two states. Let's try to see if, you are probably more familiar with, did you work with the Bryan-Ket notation before? Or are you more familiar with the wave function notation? Well, let's see some of the relations between the Bryan-Ket notation and the wave function notation. Let's look at this one, the inner product of alpha and beta. Well, this will be equal to d cubed r beta r, r alpha. I just inserted the identity. You see, this is what we had defined as psi alpha of r. If you look at this number, this inner product is nothing but r beta conjugate. But that inner product is what we would call the wave function of the ket beta at the point r. So alpha beta is equal to d cubed r psi beta of r star conjugate psi alpha of r. Let's look at the normalization. 1 should be equal to alpha alpha. Just if you look at the above line, just take beta to be the same as the alpha. Or 1 should be equal to d cubed r psi alpha of r absolute value squared. Well, let's look at what happens to the translated wave function. We had this alpha state, which we could expand in a position ket basis. This was psi alpha of r ket integrate over all the possible positions, d cubed r. Well, if I translate it by, let's say, this vector delta, this is equal to d cubed r psi alpha of r plus delta. Okay, now there is one point you should pay attention to. This translation operator acts on the vectors in my Hilbert space. That is, it acts on the kets, not on the coefficients. That is how we always define the operators. Operators are changing my kets, not the coefficients. So that is why psi alpha of r is still the same. And only the ket is changing. The ket is translated by delta. Now I can make a change of variable. Let me just call r as r prime minus delta. And so d cubed r is equal to d cubed r prime. My measure doesn't change. So t of delta alpha, this is equal to d cubed r prime psi alpha of r prime minus delta times r prime. Let me look at the wave function of this translated state. Well, the wave function is nothing but this inner product. This is my translated state. Its inner product with my position ket is what we call the wave function. This is how we define the wave function. Well, this is equal to d cubed r prime psi alpha of r prime minus delta r prime. This is the inner product. Well, that inner product is nothing but the Dirac delta. But using that Dirac delta, I can just evaluate the integral. So the wave function corresponding to my translated state is just psi alpha of r minus delta. Remember, t delta acting on r ket is equal to r plus delta. It's like active transform and passive transform. You see, if you remember our discussions on Monday, we, for example, looked at the case of rotations. I can rotate my coordinate axis in one direction, or I can rotate my vector in the opposite direction. by the same angle. The new components will be the same in both perception of rotation. It's the same thing over here. You translate the cats in one direction, that is, those are your basis vectors, or you translate your wave function in the opposite direction. This is why we have that sign difference over there. But just keep in mind that whenever we will be talking about operators in the ket space, they only change the kets, not the coefficients.
Ket space'te bir saydamlamanın mantığı ne? Dün kitapta şey okudum. Biz bu ketlere matematik çağrılığını vektör olarak değil de ray gibi vardı. Öyle bir koefficient'lar çok da önemli değil. Bu şeyler okudum. Şu an anlatım yanında ne function?
Well, you see, historically, we first had the concept of wave functions. So there are many books that talks about wave functions. And most of we will be writing about Schrödinger equations, etc. We will be solving for the wave functions. So that is why, okay, we are developing our formalism, but somehow we have to relate the new formalism to the old one so that we will be able to make transitions from one to the other one. Basically, what we are saying here is our formalism is the same thing as the wave function formalism. That is what our claim is now. It's just an expansion coefficient. I mean, you see, wave function doesn't have a special meaning. And it shouldn't have a special meaning. Why do you choose the position space? Later on, we will be working with momentum space. Or we will be dealing with energy eigenkets. Let's also do that one. Let's say we have this alpha. We know that we can expand them in terms of some complete kets. Let's call them AI. They are the eigenkets of some observable. Well, I can write the wave function of this state alpha in this form. This is Ci psi of AI of R, psi alpha of R. So this observable can be the energy. So I can write my wave function in terms of sum over wave functions over the energy. Now, if you can completely eliminate the wave function, fine. I mean, there's no problem with that. You don't want to work with wave function? Don't work with it. But, well, if you work with wave functions, you can write your equations, some of the equations we will write later on, as a differential equations. Well, mathematicians have all the machinery to solve differential equations. So once we convert them into differential equations, we can just borrow their tools. That will be our advantage. But as you said, we don't have to go to the wave functions. The position space wave functions doesn't really have any special meaning. So they're just our expansion coefficients in an expansion in the positions in terms of position kets. Well, position kets are somewhat important for us. You see, our intuition talks about the position of particles or the momentum of particles. So in quantum mechanics, we still would like to deal with exactly the same problems that classical physics solves. I mean, if you're just developing a framework which cannot even answer questions that the classical physics answers, so what's the point? So we need to somehow be able to explain with our new formalism our observations in classical physics.
Peki o zaman benim bir state için yazdığım ket ve aynı state için yazdığım wave function. Yani aynı
Well,
aynı information içeriyorlar.
yes. Well, you see, we had seen that, for example, for a given ket, you can write many column matrices. column matrices formed by these expansion coefficients. Most of them might look different depending on which basis you use, but they still correspond to the same ket. Well, the wave function is just another possible representation of this column matrix. Now let's see what this our momentum operator is. Well, momentum is a concept that we are familiar with quantum mechanics, so that's why one of the reasons why we would like to study the momentum. Now let's look at the momentum, the representation of this momentum operator in coordinate space. Well, basically we will be using this relation. Or translation by, let's say, a very small amount this time of the ket alpha. We had seen that this is nothing but psi alpha minus delta. No, psi alpha of r minus delta. Well, we know what T operator is for very small delta. We had said that it was 1 minus I over h bar p dot delta acting on alpha. This is my left-hand side. My right-hand side, I know that delta is very small, so I can make an expansion of delta of the right-hand side. And that would just give me psi alpha of r minus delta dot the gradient operator acting on psi alpha of r. Plus, of course, both sides contain terms that are proportional to delta squared or higher orders of delta. Well, let's look at the left-hand side, that is r alpha minus I over h bar r p alpha multiplied with delta. This should be equal to psi alpha of r minus delta, that the gradient of psi alpha of r. Well, this term is nothing but what we had called the psi alpha of r. So that term cancels on the left-hand side, on the right-hand side. And for the remaining equality to hold, whatever the value of delta is, I should have minus I over h bar r p alpha. This should be equal to minus gradient of psi alpha of r. Or let me write it in this form, r p alpha. This should be equal to h bar over I, the gradient, acting on r alpha. So that operator that we call the momentum should look like this when it is acting on the wave functions. Now, this is just a derivative operator that you are familiar with in quantum mechanics. Well, let's look at any questions? Well, let's look at we have some operator A. Let's look at its matrix elements. What will it look like in position space? Well, this will be equal to, I will insert two identities, one over here, d cubed r, and another one over here, d cubed r prime, r prime, r prime. So we have d cubed r prime, beta r, r a, r prime alpha, beta a alpha. This should be equal to psi star of beta, the wave function of beta ket, complex conjugated, R A R prime and psi alpha at the point R prime. Well, whenever I have a product, I can always insert 1. No. Now you see, if you have two operators, this is the same thing as A times 1 times B. Or you just put another one, another one, another one. You cannot add 1, but you can always multiply with 1 wherever you want. That's the definition of 1. It doesn't change it if you multiply it. Well, of course, now if we want to calculate this matrix element, we still need this operator. What is that operator? Well, the simplest case will be A. You can assume that this is an example. A can be some function of the position operator itself. Well, if this is the case, R, A of R, R prime, this will be equal to R, A of R prime, or A of R prime, R prime, which is A of R prime, Dirac delta of R minus R prime. What I did was, well, in this equality sign, what I did was just imagine this is a Taylor expansion of my operator. And when that R operator acts on the ket R prime, the operator just becomes R prime. Then I obtain a Taylor expansion of A of R prime. It is this one over here. Now here this R prime is just an ordinary vector. It's not an operator anymore. Since it's just an ordinary vector, it's not an operator, I can just take it out of the inner product. It is what I did in this step. Well, R and R prime kets, their inner product just gives us the Dirac delta. So this beta of some function of the operator of R, the position vector, is nothing but d cubed R, psi beta star of R, A of R, psi alpha of R. Well, here I just evaluated the R prime integration using the Dirac delta. Another example. Well, let me write it explicitly. This is, I said that this is just a Taylor expansion. So this is A of n, R operator to the power n. This is what I should understand from a function of an operator. Now let's look at how this acts on R prime. Well, I know that this is n times acting on R prime. This is equal to the operator n minus 1 times but you see this is the ket R prime is an eigenket of the position operator. So that is R prime, not the operator, but itself. So this is equal to R prime. Since it's just a number, I can just move it to the left of all the operators. I have n minus 1 operators left. Now these are n minus 2 times, and there is another one. Now this is nothing but R prime vector, not the operator, multiplying the ket. And I can just add all my operators on this R prime ket. So it just becomes R prime to the power n acting on this ket. So any power of the position operator acting on the position eigenket just gives me the eigenvalue raised to the same power. Do you agree? Do you agree? So let's see, A of R operator acting on this ket is an, these coefficients, times r to the n acting on this ket. Now this is equal to an r prime to the power n r prime. Now in the last expression over there is not the eigen, it's not the operator, it's the vector. So this sum is nothing but the function a evaluated at the vector r prime. Now, of course, just keep in mind that I'm just kind of using some shorthand notation. That you don't. This is not the Taylor expansion of a vector. This is not the Taylor expansion in terms of a vector, but the idea is basically the same. You can have products of various components, etc. So that is what I used in this step over here. Just let me do one more example and then we will give a break. The momentum operator. Well, I can just use the previous result. Well, this one is the same thing. It's just I'm instead of assuming that A is a function of the position operator only, I'm assuming that A is the momentum operator itself. So it will be just equal to psi alpha d cubed r prime psi alpha of r star r p r prime psi beta of r prime. Well, you see, we had already looked at this operator. We had seen that this is nothing but h bar over I, the gradient acting on r prime. But this is Dirac delta of r minus r prime. So alpha beta, alpha, the momentum operator, beta, this is d cubed r prime, psi alpha of r star, h bar over I, gradient, let me write with respect to r, of Dirac delta of r minus r prime of psi beta of r prime. Well, to evaluate this integral, you just do an integration by part. If you just omit the boundary terms, this becomes d cubed r prime minus h bar over I, the gradient with respect to r of psi alpha of r star, times the Dirac delta cubed of r minus r prime, psi beta of r prime. Here I made the integration by part in the r integration only. Now I can use that Dirac delta function to evaluate the r prime integral. Well, let me change my mind. Let me just do it a different way. An easier way which will not require any integration by part. This is equal to d cubed r psi alpha of r star. I have a d cubed r prime integral, but that gradient is with respect to r, not r prime. I can change the order of differentiation and integration because I'm differentiating with respect to some other variable, not the integration variable. And the boundaries do not the boundaries of r prime integral do not depend on r. So I can just write it as h bar over I, the gradient with respect to r of d cubed r prime, Dirac delta of r minus r prime, psi beta of r prime. Well, this is, I can just evaluate the r prime integral. H bar over I, the gradient of psi beta of r. Well, you see, one advantage of using the Ket-Bra and Ket notation is that when you work with wave functions, you implicitly assume that the number of particles is the same. So if you start with a single particle, well, there's only a single particle, there's a single wave function only. In this notation, it doesn't really matter, in the Bra and the Ket notation. In this derivation, the point where we assume that we are working with a single particle is when we were talking about the position kets. We said that, okay, this is my position ket, but this is the position of a single particle. So when we are saying this one, we are restricting ourselves to systems made up of a single particle. But the generalization to many particles is kind of obvious. You see, instead of this one, you can say, okay, I might have a single particle in my system, or I might have two particles in my system, so I need to talk about the positions of two different particles, or I might have three different particles in my system, or you might have as many particles as you like. And still you can talk about the kets. The kets can describe an arbitrary number of particles. Now you start describing particle creation and annihilation. That is what we see in accelerators. So this Ket notation kind of is more flexible than the wave function notation. But if you restrict yourself to a fixed number of particles, they are the same thing. Questions? Okay, let's give a break. In the next hour, we will be talking about, here we have a momentum operator. It's a Hermitian operator we had seen. It has to be Hermitian. So it has some eigenvalues which are real. We can talk about the eigenkets of momentum. And they will be complete, the momentum eigenkets of the momentum operator. So we can talk, instead of making an expansion in position space, we can make an expansion position kets. We can make an expansion in terms of momentum kets. So we will also study the momentum kets in the next hour. So that will kind of complete our first chapter, which is about the description mainly, the concepts that we will use to describe the systems. And in the next chapter, we will finally start the dynamics. How does the system change in time? Okay, let's give a break and then we will continue.